Determine if the series converges or diverges. If it converges, find the sum. So just by looking at this series, it seems that the terms are oscillating, but they're getting smaller as well. So it might be geometric. That's our first test. So the sequence that this dealt with had these terms apparently, and we want to see that in order to get from one term to the other term, am I multiplying or dividing by the same constant? And it looks like very easily we can see that we're dividing by a -3 or multiplying by a -1/3 each time. And if I do that, I get the terms of the sequence. Therefore, the series that I've developed is really a geometric series. So this is a geometric series. It didn't say to put it in summation notation or anything, so all I have to do is say whether it converges or diverges. And since r is equal to -1/3 and in absolute value less than 1, I can say the series converges, because if the common ratio is less than 1 in absolute value, it's automatically going to converge. And we actually have a formula we found for finding that sum. So the sum of this series will be the first term over 1 minus r, because it said that once you determine that it converges, find the sum as well. So does it converge or diverge? It converges. Now the sum is going to be the first term here, which is 27 over 1 minus r, and r here is -1/3. So we end up with 27 over 1 plus 1/3, 27 over 4/3, and ultimately it converges to 81 over 4. Part B, we have another series. It's not in summation notation, but they're giving us the series. We need to know if it converges or diverges, and if it converges to what. So the one that we're familiar with so far is really the geometric series. And how can I tell if this is a geometric series or not? Sometimes it's easy, unlike this one that was easy to tell. Well, I'm just dividing by a -3 each time. Here it may not be so easy, so to find the common ratio, you just have to take any a sub n over a sub n plus 1 over a sub n, and that's going to give you the common ratio. Because in order to get from one to the next, if it is geometric, you're going to keep multiplying by the same thing. Well, if you want to know what that common ratio is, if there is a common ratio, if you divide any next term by the current one, or this next term by the current one, or this next term by the current one, you're going to get the common ratio. So we can go ahead and do that for this one. Let's say I take the second guy divided by the first guy. That's going to give me 0.2. If I take the third guy and divide it by the second guy, that too will give me 0.2. If I take the fourth guy and divide it by the third guy, that too will give me 0.2. So it looks like the pattern continues, and this is a geometric series. Each time I'm multiplying by 0.2 to get to the next term. So now that I know that it's a geometric series with r equals 0.2, I know that it converges since r in absolute value is less than 1. So now that I know that it converges, I should be able to find that sum. So that sum is going to be the first guy over 1 minus r. The first guy here is 6, divided by 1 minus r in this case was 0.2, and it looks like I get 7.5 for the sum. So it converges, and it converges to 7.5. Okay, so same directions here. Does it converge or diverge? And if it converges, what does it converge to? So we could do a quick divergence test on this. If you look at this, right here we can do this two ways. If I look at the limit as n goes to infinity of 1 plus 3 to the n over 2 to the n, and when I'm looking and analyzing the limit of this, the term that takes over and becomes dominant in the denominator is 2 to the n. So I'm just going to divide everybody by 2 to the n. So I'm going to do 1 divided by 2 to the n plus 3 to the n divided by 2 to the n, and 2 to the n in the denominator divided by 2 to the n. If I do that, I'm looking at the limit as n goes to infinity of 1 over 2 to the n plus these two guys I'm going to squish together and put it as 3/2 to the n because they share the same exponent anyway, so why not? And 2 to the n over 2 to the n is just 1. So I'm basically looking at the limit as n goes to infinity of 1 over 2 to the n plus 3/2 to the n. And if I look at it that way, I know that as n gets big, this guy goes to 0. And here we have that r to the n business popping up again. And since r is equal to 3/2 and it's greater than 1, this thing is actually going to blow up and go to infinity. So the limit of the sequence does not exist. It goes off to infinity actually. So we can say that this guy, the whole series, diverges by divergence test. So that's one way we can look at it. Or if you want, we can split up the sum into, well, this guy is really just 1 over 2 to the n plus 3 to the n over 2 to the n. We can say that's just two of these guys. So I'm going to look at it as such. And then say, well, let's look at them as two separate sums. 1 over 2 to the n plus, I'm going to put them together as 3/2 to the n. So very similar to how we analyzed it before. This, we should know that if we spit out some terms, each time we're multiplying by a half because it's 1 over 2 to the n. So this is going to be a geometric series with r equals a half. Again, if you spit out a few terms, you're going to get a half, a fourth, an eighth, 1 over 16, and so forth. And since r is less than 1 in absolute value, this guy is going to converge by itself. However, if I look at this guy, this too is going to be a geometric series. And r for this guy is 3/2 because the first term is 3/2, the next term you're going to multiply by another 3/2, another 3/2, another 3/2, and so forth. Here notice though that r is greater than 1 in absolute value, so this guy diverges. And if one of them converges and one of them diverges, the whole series diverges. So we can either do a divergence test or split it up and look at it piece by piece. Same directions, does it converge or does it diverge? And if it converges, then what does it converge to? If I do a quick divergence test, if I pull this guy out and I go to the side and say, let me see quickly like before what happens here. I have 5 to the n, 2 to the n. Notice n gets big, so I have 5 to the big, which is big. 3 over big is going to go to 0. And 2 over big, as n gets infinite, is also 0. So this goes to 0, and I have no conclusion. It doesn't help me like it did for the previous problem. So I'm going to analyze it by looking at it in separate pieces. I have this guy plus this guy. And this we should recognize as just a multiple of the harmonic series, for which we know it definitely diverges. So we'll say this diverges. And I can't conclude automatically, remember, that the whole thing is going to diverge, because if this too diverges, then together maybe they won't diverge. So I have to analyze this. And if this is bothering you, just spit out a few terms and you'll see that that definitely is a geometric series. So if n is 1, I have 3/5. If n is 2, I have 3 over 5 squared. If n is 3, I have 3 over 5 cubed, and so forth. So it definitely is a geometric series with the first term being 3/5, and r, each time it looks like you're multiplying a 1/5. And r is less than 1 in absolute value, so this guy, the left side, converges. Left side converges, the right piece diverges, so the whole thing, as a result, the whole series diverges. You analyze it piece by piece. Remember, if one converges, one diverges, the whole thing is going to diverge. Okay, does the series converge or diverge? And if it converges, what does it converge to? Again, divergence test is usually a good first test to quickly try out before you do anything else. So when I apply the divergence test, I look at the limit that's going to be big over big. Infinity over infinity says I can apply L'Hopital. So when I apply L'Hopital, I get e to the n over 2n. That's still going to be infinity over infinity, so I'm going to apply L'Hopital again. That's going to be e to the n still, and the denominator is going to be 2. Now I'm going to get infinity over 2, which is infinity. So I just found that the limit of this corresponding sequence does not go to 0, which means I can make a conclusion right off the bat and say that the series diverges by the divergence test, and I don't have to go analyze it any further. So this series, again, I can start going and looking at the divergence test right away to see if it converges or diverges. But I do see that I have a 4 to the n on top, or negative 4 to the n, and a 5 to some n involved. So I'm already thinking that that's going to be a 4/5 to the n and is eventually going to go to 0. So even if I do this test that helped me with the previous one, it looks like this may not help me. Whenever you have a number raised to some power of n, maybe there's hope that this is a geometric series. You can spit out a few terms to see what happens, just to make yourself feel better. So let's spit out a few terms and see what happens. So notice if you spit out a few terms, you can see that each time to get to the next term, it looks like I'm multiplying by a 5 in the denominator, and it looks like I'm multiplying by a negative 4 in the numerator. So it's plausible that there's a negative 4/5 as the common ratio. We can either just pull it out of there, the way we see it, or we can try to rewrite this into a more manageable form. So I will go ahead and use some exponent laws. I'm going to split the 5 to the n times 5 to the negative 1, because if they have the same base and I add exponents, I'm going to get back to n minus 1 anyway. Then I'm going to say I'll leave the 5 to the n downstairs, and this guy has a negative exponent. I'm going to shove it upstairs, and it's going to become 5 to the 1 upstairs. Now, if I want, I can even take that outside or leave it inside. It's just a constant 5, it doesn't matter. And both of these guys have a power of n, so I can sort of merge them together, and that's what was happening here when you were spitting out the terms. So whenever in doubt, spit out some terms. That's negative 4/5 to the n. So now it's pretty clear that I have, if n is 1, 5 and 5 cancel, and I have my first term just be negative 4, as we had seen before. And each time, a power of negative 4/5 is stacking up. So this is a geometric series with r equals negative 4/5, and since r in absolute value here is less than 1, it converges. And we know what it converges to. It converges to the first term over 1 minus the common ratio. First term here again is this guy. You had already spit it out. Negative 4 over 5 to the 0 is just negative 4 over 1 minus the common ratio is negative 4/5. So we get negative 4 over 1 plus 4/5, and I'm just going to multiply top and bottom by the denominator of 5. That's going to give me negative 20 over 5 times 1 is 5, plus 4. That's going to be negative 20 over 9 that the sum converges to.